Hi everyone. So in this video lecture, we're going to talk about sampling theorem, and one of the subscribers, actually this request came from one of the subscribers. I'm not sure if this person has subscribed or not. If you haven't, please do subscribe. And so I got this comment asking, so somebody has asked me to create a video on sampling theorem. So hi, this video is for you. And so I'm going to explain what sampling theorem is. I'm not going to go into the maths of it. And at the end of the video, like when you watch the whole video, when you have watched it, you can let me know in the comments if you have any specific question, like if you want me to go into the maths of it. But I believe it is not necessary, because if you are already into digital image processing, all the concepts are already clear. And most of the times when it comes to sampling theorem, the problem arises when we're not really clear as to like how, like what where can we use it, or what this theorem actually stands for, right? So I am creating this video from that standpoint, and if there is anything else, you can let me know, obviously. So let's start. So first of all, this is sampling theorem, right? So we have sampling word here. So first of all, I'm gonna talk about sampling. And if you have already watched my previous videos in the playlist, if you haven't, you can check the playlist digital image processing and check that video specifically created for sampling, right? So sampling is all about spatial resolution, right? So what we are doing is we are converting an analog signal into a digital signal, right? There are samples in digital signal, right? So now analog signal, is in the form of continuous signal, like continuous waveform, right? Like there is no discrete quantity. And when we talk about digital signals, digital form, it has discrete shapes, discrete in the form of like numbers or digits. Okay, so for example, a person is analog data. I hope you know that, right? What is analog? Like analog is like everything physical, basically. And so when you click picture of that person, an image is generated. So suppose this is an image, right? And let's say this is actually analog image, because we can have analog image, we can have digital image, right? So suppose this is analog image. So again, I'll give you an example. For example, images you see on TV, when you watch TV, those are analog images, because some electrical means are manipulating those images with electrical signals. Okay, and because of that, those manipulations performed by those electrical signals, there are always some sort of variations that can be shown in the form of a waveform, continuous waveform. Okay, so now when this image, when it is converted into digital form, and I hope you know what a digital image looks like, right? It looks like collection of squares or boxes. So for example, this one, right? This is how digital image looks like. Again, you should watch that previous video where I've explained the concept of digital image. We have pixels and everything. So this is how it looks like, right? It is usually when we walk with it, it looks like a collection of squares or boxes. So when analog signal is converted into a digital signal, samples are created. Okay, and this process is called sampling. So what is sampling? You understood, right? So for example, this is analog signal and this is digital signal. How did you obtain it? You take samples, right? So this is and I'm assuming, and I hope you know, that we'll talk about time variations here, right? So this is continuous, right? So at different intervals, so this is your timeline, right? Like time. Okay, so at different intervals, you take these samples. These are the samples taken. Okay, and if you want, like if you go like this, you'll see that original signal can be constructed, right? Original signal can be constructed. So what is sampling theorem? Now let's go back to the topic. What is sampling theorem? So first of all, you had an analog signal. You converted into digital samples or digital signal, and according to this theorem, the signal is now in the sample or digital form. Okay, right? Signals in a digital form now. Now, if you want to reconstruct the analog signal from this signal, can you do that? Yes, you can. It can now be reconstructed back to analog form from these given samples, right? I already showed you how, like this. Okay, so it can be done, but it can only be done if the frequencies of the original signal were less than half of the sampling frequency. Okay, so understand what it says. What is frequency? Frequency is the rate at what is frequency? Like, it is the rate at which something happens, right? So for example, in this case, so what is sampling frequency? Sampling frequency here, when you're creating samples, what is sampling frequency? Sampling frequency means in 1 second, like how many samples can you create in a given period of time? Okay, so number of samples taken in 1 second from the signal. Okay, that is your sampling frequency. How many samples can you create in 1 second? Okay, in simple terms. So sampling theorem means that when you have the digital signal, because you used sampling frequency here, you created, so for example, let's say in 1 second you created 3 samples. Okay, so that becomes your sampling frequency. Fine. So sampling theorem says that you can reconstruct this analog signal from this digital signal if the sampling frequency that was used here, okay, if this sampling frequency was less than no, the sampling frequency should be more. So yeah, if the sampling frequency was more than double of the original frequency. Okay, I'm not sure if I said it right the first time. So basically this theorem states that you can create your analog signal back from the digital signal if the sampling frequency is more than double the original signal frequency. Okay, or in other words, the original signal frequency should be less than half of the sampling frequency. Okay, because this original signal also has some sort of frequency, right? It is a continuous wave. It has certain kind of frequency rate at which something is changing. So this is this one. You can note this down. Fine. Your sampling frequency should be more than or equal to twice original frequency, or your original frequency should be less than half the sampling frequency. Okay, and when you come across numericals, usually if in the original signal, obviously the signals are like there in this signal, do you think frequency will be the same? No, there will be many frequencies. There will be different frequency components, right? So in that case, you have to choose the maximum one. Okay, in the original signal, there are many frequencies or different frequencies or different components. So you have to choose the maximum one when we are saying original frequency. So you have to choose the maximum frequency. Fine. And then I also want to talk about another concept associated with it. So at this point, I'm assuming that you already understand what sampling theorem is. like the base should be strong, right? So that's the whole funda behind it. So I want to talk about another concept that goes with it. So that's aliasing, right? It's called, it's not written anywhere. So let me write it here. Aliasing, okay? Right? So we have these two terms, aliasing and alias. So in simple words, what is an alias? Alias means like duplicate, okay, or a pen name. Fine. So it's not the original name, it is a pen name. That is what an alias is. Fine. And aliasing is the effect. Now, aliasing, we are talking about digital image processing. So in that sense, what is aliasing? We are again talking about we are talking about duplicates, but duplicate name or what? So duplicate frequency. So aliasing means that a frequency has a pen name or a duplicate name. What I mean here is that you have a frequency, fine, in the continuous signal, right? So it has frequency, fine. When you convert it into a digital signal, the same frequency is distorted and it appears as many frequencies. Okay, so for example, this is analog signal, this is digital signal. Suppose this is how the samples are created. So first sample, second sample, then we take third sample, fourth and fifth. Okay, now here when these samples were taken, if we trace them, original signal can be created, right? But in this case, if you trace these, do you think original signal will be created? It's gonna go like something like this. I mean, you see, so if wrong samples are taken sometimes, okay, the actual frequency in the continuous signal will be distorted in the digital signal. Okay, and sometimes it appears as many frequencies, and because of this distortion, so for example here we have taken less samples. If we take more samples, like there will be many frequency components in the digital signal as well. So because of that, and you know that digital signals have bits, we work with bits, right? We work with pixels. So because of this distortion, the impact will be on the pixels, okay? And it's actually going to affect the number of pixels needed in the image to actually represent the image perfectly. Okay, so there will be some kind of distortion. And sometimes it's visible, sometimes it's not. Sometimes, when you see a picture, you find it a little distorted or something. So this happens when sampling theorem is not followed. And that's where you need to use filtering. Filters are used, and those specific extra frequency components are removed so that image can be as close to its original form as possible. And because if you see, if the digital signal is distorted when you're performing the conversion, if the digital signal is distorted due to those extra frequencies or something else, there will be inconsistencies, there will be disparity when you try to construct the original analog signal from this digital signal, okay? Because there are already some disparities, and when you try to, like in this sense, so when you try to construct the original signal, there will be inconsistencies, it will not be in its the purest form, right? So that's where sampling theorem comes. So if you work with sampling theorem, it provides you with this condition that if you really want that the whole conversion process from not only analog to digital, but back to analog form from digital, if you want that this whole process results in disinfected or uncorrupted signal, the sampling frequency should be more than or equal to twice the original frequency. That's the basis of sampling theorem. So With that said, this is a very simple concept, and I hope it helped. And if there is any doubt, if you want further explanation, please let me know if you want me to go into the maths of it. But I'm pretty sure that that will be very easy after you understand this concept. So anyway, still let me know if there is any doubt or if it was helpful in any way. I'll see you in the next video lecture. Till then, take care.